First of all, I promised you to show the videos about segmentation using neural networks. Let's begin with those particular videos. They are simply about this is the demonstration of one of NVIDIA algorithms. Well, there are two parts. On the first part, this is just happening the segmentation. On the second part, they apply some identifiers for every object on the screen. But generally, if this is possible, then everything else is just the extension. So as well as we did for how to say it, for OpenCV, we detected specific not images, specific part on the image with a known color or known shape. The same task could be processed, or the same part could be processed to neural network, and it would do exactly the part for segmentation for us. Of course, you can see that sometimes there appears some noise, and if there was not a neural network but some regular algorithm, we would receive less noise. But this demonstration shows that everything works pretty well. In the real life, for any data set, most likely we won't get these accurate results. More likely we will get something like this. For if we, for example, train our neural network on a specific data set and apply it to other circumstances. For example, with another light, with another environment, most likely we will get a lot of noise. But this, what you see on the screen, still should be considered as correct work, because generally this works fine. There are some specific estimations how to say that segmentation worked correctly or not. But as a human, we can say that generally it works more or less fine. Well, it just appeared the question in my head. It is possible to make exactly these things without neural networks. Just if we would know the how to say, the interval of the color for the road, for the sky, for the building, and so on, then it will be easy to detect well-known parts on the road. Applying machine learning is just another way to do it. Which of them is easier? I don't know. It depends. It depends on the specific circumstances for applying the algorithm. Okay. That was a little bit of extension for the previous lecture. Now about today's idea. Today I will talk about, once again, I have to draw the whole pipeline of the autonomous driving. Maybe you already remember all the steps because I draw it almost on every lecture. Here we have perception with machine learning or with just OpenCV or some kind of image processing. Here we have localization. Here we have just environment. There is no a specific step of the algorithm. Here we just get some information from the environment. Then we have to fuse it somehow, and then we use the motion planning. And today we're talking exactly about motion planning. So today we will have almost today we have the last informative lecture. On the next week, we will meet for, I don't know, 15 minutes, just for me to show how to do the last homework. But today we will describe the control and navigation part, planning and so on. Okay, what's the process of this mysterious mysterious part that's called navigation? Well, exactly, there are two most common steps. First of all, we have to create a path, and secondly, we have to follow this path. Yeah, thank you. We can explore the environment during movement, but still, for exact navigation, we should assume that we, in every moment of time, know the exact environment, exact map of environment, and exact position. Without these attributes, we won't be able to navigate correctly. It is possible that we created the path and we did it for the wrong map. For example, we previously built the map incorrectly, and but we created the path in this map. And during movement, we solved simultaneously with navigation localization problem and understood that map is built correctly. Then we have to update the map, and furthermore, we have to update the path. But in general, let's just think that we don't consider map building process. We think that it is done for us somewhere, somebody would do it. Well, the easiest solution, the easiest problem where you can face the navigation problem is following the path, the exit, finding the exit in the maze. And I guess if you watch precisely on how does this robot behave, I think you will find out which algorithm does it use to find the exit from the maze. Let's look at it. We don't know if it builds a map. We don't know anything. We just can guess. If you find out, you can write your idea in chat. Well, this maze is not very complicated. Well, any ideas? How do you think? What's the how does it try to solve the maze, the labyrinth? No ideas? Well, let me run it at twice speed. We discussed build a map and adapts its previously seen places. Last algorithm we discussed, it builds a map. What do you mean by the last algorithm we discussed? On the previous lecture or what? Yes, the last algorithm of the previous lecture is always build the map. But this one, we are not sure about this. We can just think about its behavior. Well, this algorithm is very easy. It just picks the turning right if it's possible. So it just moves along the wall that is on the right hand of this robot. It never turns left if it sees the T intersection. If it comes from here, it won't rotate to the left at any time. It always chooses moving along the right wall. And this is the easiest way for navigation. Move while it's possible. The extension, another field area where you saw the similar approach, where it is correctly used, is for automatic vacuum cleaners, robot vacuum cleaners, who are that uses they don't use slam. They just move forward until they hit the wall, then they rotate on some angle, move until they hit the wall, and so on and so on. They just move forward well they can. But suppose if it's in left, so for any structure of the maze, there is the interesting law. That law is very loud word. For any maze, for most mazes, the moving along the right wall will always bring us to the exit. Let me show you the example. For example, I will draw the random maze. Let's do it in this way, that will be pam 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 pam. Can we draw description tree to discover? You shouldn't draw the description tree. I mean that this was I just wanted you to show the algorithm that is very simple, and I want to demonstrate why is it simple and why is it powerful. Well, we have some maze, okay, where we have the enter and we have the exit. And I want to prove that always choosing the turning right if it's possible, we will always find the exit. Well, okay, we appear here and we move forward, we move right and move along the right wall. Okay, then we rotate, we move along this wall, and then we move here, here, here. Then we face the dead end, but we still turn to keep the wall on the right hand. Then move here, and here. Then we move over here. I think I just thought that I could draw the path in another color. So we move along the right place, the right hand. Come on. We move from the right hand. We move it over here. Then we go. Then we move it again. We move for the right place, and how we find the exit. It's always possible. The only way when it is impossible is if we for some reason appear near this structure. Well, there is some maze around us, and we for some reason appeared near the kind of closed area in the labyrinth. Then choosing the right hand will bring us to the infinite loop. If we can somehow be sure that we have no loops here, then moving across along the wall on the right or on the left hand, but you have to pick one of the rotations before you start, will always bring you to the exit of the maze. There is interesting fact about Minotaur maze. in the ancient Greece, there was the maze. I don't remember for each exactly hero of Greece, but there was the infinite. They thought that there is the infinite maze. Let's consider that its radius is several kilometers, and it was said that this maze drives crazy everybody who tried to solve it, because it was just large, and you have to move through very long distances with no changes in this maze. But you can copy this image and try to solve it in Paint, keeping always the right wall, and you will always solve it. Of course, there are more powerful algorithms for solving mazes, but this one is just as easy as powerful. Of course, if you're talking about fast solution, we won't use this kind of algorithm. But if we just have to find any solution, we can use it. Okay, let's now let's just talk about more powerful algorithms. To avoid redundant moves, I mean to find the most optimal path. If we have the beginning point and the ending point, we have to draw the path that would be both as fast as possible and as safe as possible. And to complete this, we have, not we, but the general approach is to have two different parts for planning, global and local. The idea of global planner is to build several points from the beginning to the end where we should appear during the movement. So we don't think if it's possible to reach one point from another in the shortest way. We just build several points and we say, okay, you have to pass through every points on this path to achieve the finish point. And the idea of the local planner is to take two successive points and create a path from one to another that would be safe. So in the beginning, I said that if we want to build the fast and safe route, then the global planner thinks about fast route, and the local planner thinks about safe route. Yes, and now let's look at the global planner more precisely. The idea is we have to build the trajectory. Well, we don't know how far these points on the trajectory should be, but in general, that should be the trajectory. And the idea how to do it is very straightforward. We have to consider our map as a graph where nodes are coordinate cells and edges are some kind of connection between these nodes, and the weight of these edges would be the cost. How much we should we pay for moving from one cell to another. So basically, if there is the wall on the way, then the cost to come from the free cell to the occupied cell should be infinite or very, very large. And the cost to come from the one free cell to another free cell should be little. And then we can, if we consider the map as this kind of graph, then we can build any path. And I hope that you know a lot of algorithms that build the path for such structures. Well, they're described on the slide. The easiest are breadth first and depth first. Well, then also well known the greedy algorithm, and You also know about Dijkstra and A-star algorithm. Fun fact that for the large graphs with random weights, there was research that the greedy algorithm brings it doesn't bring the optimal weight of the path, but its weight is only 10% lower than, no, 10% greater than the weight of the optimal path that is built by Dijkstra or A-star algorithm. But the complexity of the grid algorithm is much lower. So in general, if you have, just for you to know, if you have some kind of large graph where you have to build the path, and you don't want to program a lot, and you are not you don't worry about the super mega optimal cost of the path, then your best choice would be grid algorithm. But let's look at them more precisely. I hope that everybody of you remembers the Dijkstra algorithm. Let me just a little bit remind you that on every step, you should consider all possible, how to say it, steps, where it can move from one point to another. And it should calculate the weight, how to reach from the very beginning one position or another. And it always have to choose the lowest weight to keep it in mind. For example, if you want to build the path from position 1 to position 4, it should consider this way, this way, this way, this way, and all the possible ways, and it should calculate all the possible weights for this way to find which of them is cheaper. Yeah, so here, for example, it found just that moving from 1 to 6 for 14 is more expensive than moving first to 3 than to 6 for 11, and so on. In the end, it will build the shortest path. It always builds the shortest path, but it has to look through every node, and as far as I remember, its complexity is like quadro. I don't remember complexity. What? Dijkstra algorithm complexity. Algorithm, really? Time complexity for the matrix representation. This is more looking like truth. Yeah, the Dijkstra algorithm has the complexity, the quadratic complexity. I guess that just in this paper that described the algorithm with the logarithmic complexity. Okay. Okay, let's go further. I hope that you know also about A-star algorithm. If you don't, then let me describe it. So the idea is that it also looks on the cost from one node of graph to another, but except of cost, it also calculates the heuristic function. So the cost, how to say it, how to come from one node to another consists of two parameters. First of all, the cost of moving from one node to another, and then the cost of every particular cell, how far is it from the exit. So the second part can be calculated knowing only the exit. Even if we don't know the point where we should start, if we have only map and the destination point, we can calculate the heuristic function that shows us how far is the exit from every how to say it, from every cell in the map. And then combining these two parts, so from the very beginning we have to consider once again every possible point, every possible cell, and we have to look which way would have the lowest risk combination on every step of algorithm. Well, let me show you the visualization. We start it's a GIF animation, so it's have to start from the beginning. This is the initiation point. This is the starting point. Let's look at it once again. So first of all, it moves as well as greedy algorithm just forward. Then it tries to look through every possible other points that could bring us to the exit. And it comes from the points with the low weight to the points with the highest weight. There is some kind of research how this algorithm, greedy, A star, and breadth first, how are they compared in different mazes? It's just interesting. I think you never saw visualization of such algorithms. First of all, it shows that there is some random maze, and let's find out which algorithm would find the route faster. This is the breadth first algorithm. Yes, you see that it is almost brute force. It looked through almost every cell. This is the greedy algorithm. It just looks. It chooses that direction that is closer to the end. Let me show from the beginning. So first of all, it found this position because it's closer. Then they compete two possible ways that they both are far from the end, but it comes for one cell for every area of search. And once again, it will find, I don't remember whether this or this, that brings us to this position that is also seems to be close to the exit. Here it is. Well, not this, but this. It found that going over in this way, these points are closer to exit than this one. That's why it tries to find the exit somewhere on that way. And after that, it started to look in this way, and then found the exit. That worked faster than for the breadth first algorithm. Let me show it once again from the beginning. This is the almost brute force algorithm, where we looked in the bad way. We looked on every cell. This is the best first algorithm or greedy algorithm that also looked a lot, but it works a little bit faster. And the A star algorithm that also might work as slow as previous. But if you look on other graph structures, this is the breadth first, this is the best first, and this is the A star. Well, and the lower we have obstacles on the graph, the better we have the best first algorithm. But A star is also performs well, especially on the end of the path. And once again, the comparison of A star and Dijkstra on random mazes. Here we have A star, here we have Dijkstra. Once again, we can find mazes where Dijkstra will always win or where A star will always win. The idea is not to to choose which algorithm is the best in the world. The idea is to find out which works better in most time. Most times is not correct English construction. You understood what I meant. Which in general works better. Well, we can say for these random mazes, most likely A star worked better. Interesting. I never saw this part of this video. I'm just curious what will happen next. I think that here should again a star should win. You see, fun. Well, yeah, that depends on the starting point. Okay, just some video. Okay, I hope that you understood about global planner. Its idea is just to build the path through the nodes, some kind of node. We can by ourselves determine what are the nodes. Its idea just to build some points that we should visit. But visiting of this nodes is the task of the local planner. If we have point of the beginning and point of the end, we should move our car or robot in that way to avoid not to hit the walls. And moreover, we have to find out if it's even possible, if the global planner didn't make a mistake. That's why local planner works more closely to the localization part and to the motion part. So the idea is just to keep our car or robot as close to the trajectory as it's possible, and to avoid the walls. But how can we do it? If, for example, for some reason, that is the next slide. If for some reason we found that our trajectory should be this way, but we are somewhere not on the trajectory, how can we come back to the correct trajectory? There is the approach that is called PID regulator. Oh, by the way, we have only 5 minutes till the end. Let's reconnect now before I start to explain about PID regulators. Okay, let's reconnect and carry on. Let's assume that on every step we know the distance from the real trajectory. How can we return to the trajectory if we know the error on every path, on every time step? Well, let's think that we don't know anything about PID regulators. Let's just come up with a new idea. Okay, so once again, task. We have the well-known trajectory, but we are not on the trajectory, but we know the distance or even the rotation. Is it true that on every period of time, for example, if we this far, the error function is this high? If we, for example, over here, the error function is this high. Is it true that on every step, the further we are from the trajectory, from the real trajectory, the greater we have to rotate? Well, I guess it's true. So if we are somewhere here, zoom cannot rotate it, yes. Okay, if we are here, we have to rotate on the left lower than if we are here. Yes, the further we are from the real trajectory, the further we should, the more we should rotate for faster joining the whole trajectory. Okay, let's do exactly this, and only this. Let's think that we should rotate move our wheels on the value of the error. Of course, at some way, for this particular case, if we just rotate our wheels let's think that wheels of our robot are like this, and we rotate them on E, for example. Yes, and then after some time, we will appear to be over here. Still, the wheels are rotated. They rotate a little bit more because we rotate our wheels every timestamp on the different value, because E, while rotating, it is a little bit changes. But there appears a situation when we just move along, not along, but we cross the line, and instead of being rotated correctly, we're rotating something like this. Well, it's clear what to do then. We have to rotate in another way, in another, how to say it, turn. And therefore, we'll move something like this. Something like this. We will always, how to say it, we will always come to the real trajectory. This amplitude will always decrease. Well, this is just the mathematical law. But in general, our approach would be like this. We also can keep some kind of coefficient for this linear function. Yes, we have the error in every moment of time. This is a function that depends on time, and we just multiply it for some coefficient, maybe that is equal to 1, maybe not, doesn't matter, some proportional coefficient. And our how to say it, influence on the moving is just proportional for our error, and this is P and P in PID regulator, proportional. Then we have to a little bit smooth. We want to smooth a little bit this trajectory. In our dream, this trajectory should be like this. Like this. Well, in our dream, it should be like this. When we, as fast as possible, return to the trajectory and move along this trajectory. But at least it should be like this. Well, we did another thing. It is a little bit close to what we wanted, but still, how can we update it? When we can add the differential. Yes, the idea is that we can look at how fast the error function differs, and the faster it changes, then it means that we are rotated more perpendicular to the trajectory. Yes, if let's look at this more precisely. If we move along the trajectory, then the error function doesn't change with the time, and the derivative of this error function is 0. But if the derivative is high, which means that the error function changes fast, in which cases the error function changes the fastest. When we move perpendicular to the trajectory, to the ideal trajectory, and if it changes fast, then we have to a little bit slow down our speed. Yes, because we don't want to cross this line very fast. And this is D and PID regulator. We just add some differential parameter. And I hope that you already know that what is E in PID regulator? It's integral. It also adds some coefficient that depends not on the derivative but on the integral from the error. And that's it. And in this picture, you can see the difference of using only D part. This is black. The green part is using both D and P and D proportional. No, from the beginning. Green is using only proportional. D is using both proportional and differential, and K is using 3 of them: proportional, differential, and integrational. You can ask why using two of them, using both differential and proportional, is worse than using only proportional. That depends on this coefficient. Here you can see if we change the values of proportional, integral, and differential, how we can change the signal. And this is a very easy approach. This approach, it was developed like 40 years ago, if not 60. It's like a very old approach. But I visited one conference where there was the one professor whose main idea of his report was that there is nothing more efficient than PID regulators when we're talking about trying to keep the trajectory. Of course, there are some algorithms that try to do the same way, let's say the same thing as PID regulator, but in general, it is the most powerful algorithm for returning the trajectory. So basically, that is all. There is nothing more complicated in moving of the robot. Yeah, we have to plan the trajectory, and we have to keep this trajectory. What can go wrong? If our trajectory moves through the wall. In this case, we have to rebuild whole path. And then we have to apply PID regulator. And that's it. This is really all about moving. There is nothing more complicated. Even in Tesla cars, the videos that you saw, the most challenging part is to build the trajectory of movement. The movement in the end works according to PID regulator. That is why sometimes you can see that if this regulator is not set up very precisely, that sometimes autopilot car moves like this along the trajectory, especially after some rotating. If it rotated, it understood that for some reasons it doesn't move across the optimal trajectory, and it tries to return to the trajectory. It does it with some harmonic way. Of course, it's very it stops to be harmonic when you very fast, but several harmonics you can find out. You can find on these videos. Okay. Are there any questions so far? If not, then lucky you are, because now you know everything about how the autopilots work. Of course, there are a lot of questions about the programming implementation of each part, but in general, the high-level view on autonomous driving you already have, and there is nothing more complicated here. Of course, on every part there might appear some heuristic algorithm or so on, but in general, it's just the perception. It's only finding out what's going on outside, where the all the objects in the environment, where the obstacles, where the road. Is just the localization. We only want to know where we are exactly. We can use GPS, we can use odometer sensors, we can use scan matchers that compare the new coming data from scanners, from laser scanners or for camera that impose it on the map. And there is nothing more, nothing complicated in moving. When we found out our exact position, we just know where we want to move. We know our destination point. We build a path and avoiding all the obstacles. This path should avoid all the obstacles. We just have to follow this trajectory, and that's it. This is how the autopilots work. Okay, today's lecture was also short. On the next lecture, I will present you the final task. It would be the task in the Moodle that would require some programming from you, and you will have to move. You will program the little car that should move until it faces the obstacle. You will have to recognize the obstacle on the video. This little car is equipped with the video camera, and you will be able to receive the video frames. I will show you how to do it. And your task will be to stop when it sees the obstacle. There will be an obstacle on the road, and you will have to move until you face the obstacle. That will be your task. So basically, we'll have two tasks. First of them is to run ROS. Second, I will present you on the next lecture. You have to complete both these tasks to get access to the exam. On the exam, we will speak a little bit about the theory. I'm not sure if I will have some questions for the exam, but I hope I have to prepare them. Okay, the general idea. This is practical task or just programming. This what's the difference between practical task and programming?
Good afternoon, teacher. Teacher, I have a question.
Yes, sure.
It's not in the lesson, but I always badly and start ROS software. I don't know why. I try more than 10 times. I don't know. There's a lot of problem. I understand badly.
Can you write me the?
Can you help me, please?
Can you write me an email with logs and screenshots of your problem? Okay.
Okay. Okay.
Just
and I want to.
Okay.
I want to request you also. That's why I don't send any task.
I understand. Okay. So I understand that you have some questions. Please write them down. I will explain it in the email.
In Gmail, okay.
Do we have to write theories in the exam, or it will be the project basis credit? You won't have to write any theories. We'll just have a small talk.
And we have an exam right now, or for next week, next month, isn't?
The exam will be in the end of the next month, somewhere in this December.
Okay, thank you.
So you have the time until the end of the December to complete the ROS task and the task about this one that I will present on the next lecture.
Okay, we have a task for next lecture.
Yes, on the next lecture I will present you the new task, the second one.
Okay. Yeah.
Okay, are there any more questions? I mean, saying like total moving or real robots moving. Second task. There would be the simulator that you will have to program the behavior of the real robot, but in the simulator. So basically, it would be more complicated than moving turtles, but the high view on this would be the same. You will just have to send the command, send the robot several commands how to move according to the data that it captures from the video, from the video camera. Okay, any more questions? Okay, great. If there are no questions, then thank you for your attention. Please don't hesitate to contact me in email if you have some troubles. Even if you didn't start the first task, it's still okay to write me then that you have some problems. We'll fix it them in the email.
Teacher, are you great with me? There is a 3 task for first lesson.
Say it again from
right?
the beginning.
First lesson, the right one, the blue one, the lecture who have a blue.
Oh, yes, lecture. The first lecture about was so.
There is a 3 task.
There is one task
inside.
Well, okay. Let me open once again. This. Let me open this lecture.
I will show.
If you look precisely on the video where I presented.
Yes, I flew to the YouTube. I know.
There I was talking. I was talking that. Where is this? Okay, wait a second. Wait a second. I will find that lecture. I'll find that lecture.
That's all.
In the slides, there are 5 tasks.
There's
1,
a 5 or
2, 3, 4, 5. But you have to solve only one of them, only this one.
The last one.
Yes. Because first 4, I solved on the video.
Okay.
We together program this one.
I
this.
saw it in YouTube.
And this one, the only one that we didn't program, and you have to do it by yourself. I mean.
Okay, just the blue one. This task, question 5.
Yes. Okay. If there are no more questions, then thank you for your attention. Once again, from the page.
There are tasks to the 2 last time.
Say it again.
I mean, hello?
Yes, say it again.
You are with me?
Yes.
There is a task for location and SLAM.
Did I send you any task about SLAM? I just don't remember. I think not. I'm not sure that I sent you anything about SLAM. I won't find it in the mails. Well, there will be no task about SLAM. So no, Navin, you are wrong. You have to complete exactly this.
Okay, Tinja, when I install now, when you will resolve me and you help me to install the rows, there is a 1 task, means the question 5, right?
Yes.
Just only this task.
Only this.
Or there is another task also.
And
that will be that I will make.
Now, right now, you have only 1 task, this one, and on the next lecture, there would be the second task.
Okay, thank you so much. I understand. So, okay. Okay, thank you.
Okay. Navin, now the task is from page 31, because the task from page 27, this one, I solved on the video, on the lecture.
You already done.
Yes. I just okay. All right. Are there any more questions? Great. If there are no more questions, then once again, thank you. See you next week.